You have assignments for me, 27, 28, 31. Send them to your left. So this problem is in chapter 3, section 1. Matter of fact, this is the one you asked about start class yesterday. And we decided that the best way to solve this problem was to rewrite it and multiply it out. So if I change this to x to the 1/3, I can then move that in. Here I have x to the 1/3 times x to the 1st. So I get x to the 4/3. And everything is a power. I know what to do here. But if I want to treat these separately, I run into an issue. I think this example is a little harder to work with. So let me do this. Let's consider these two functions. F of x is x cubed, and g of x is x squared. I know how to take those derivatives. What's the derivative of x cubed?
X squared.
And the derivative of x squared is just 2x. But if I multiply f times g, that's x cubed times x squared. And when you multiply with the same bases, you add the powers. The derivative of that would then be 5x to the 4th. But f prime of x times g prime of x, 3x squared times 2x, that's not right. I would really like to try and do the same thing I was doing for adding. When you add things, you just add their derivatives. When you subtract things, you just subtract their derivatives. When I multiply things, no. All right. How do I figure out what's going on here? And I know there are lots of algebraic justifications. If I really wanted to, I could go back to the limit definition and say, if I'm multiplying two things, how do I split them up to do all that limit work? The algebra involved makes my teeth itch. I hate it. So I'm going to cheat. Imagine I want to think of multiplying two things as building a rectangle whose sides are the two things I'm multiplying. This idea of multiplication as turning things into areas goes all the way back to Mesopotamia and Babylon. This is 6,000 years old. Now, when we think of a derivative, we're thinking of changing the x value, right? I'm going to make an assumption. If I go from f of x to f of x plus h, that f is going to get a little bit bigger. So f of x plus h will be a little bit bigger than f of x. G of x plus h will be a little bit bigger than g. This should actually line up here, so those should be connected. These should, this screwed up the box. Stop. Let's try this again. I want the box to be bigger on two sides. So we'll make it a little bit bigger on this side and a little bit bigger on this side. So I have this little excess L shape here. So this is f of x plus h. This is g of x plus h. And the inside brown pieces, this is g of x, this is f of x. So we're going to ignore this stupid mess over here for now. Okay. I look at that L shape on the outside. And I'm going to break that into three little pieces. This top piece here, this side piece, but instead of doing this whole thing, I'm going to chop it so I have this little corner here as well. So that became three pieces: a long rectangle across the top, a tall, skinny rectangle along the right side, and this little square in the corner. A question for you. This change right here, just that little piece, that's g of x plus h minus g of x. Doesn't that look like it's our derivative? That's just the change in g. And this little piece right here, that's f of x plus h minus f of x. That's just the change in f. So if I think about this upper rectangle right here, f doesn't change. Only g changes. What about on this side over here?
G doesn't change, but F does.
And in this little upper corner, they're both changing. Kind of hard to see. I wrote both up there. But I want to look at what happens as h gets smaller and smaller and smaller, right? And h is really affected by how far apart the top blue line is from the top brown line. It's affected by how far apart the right brown line is from the right blue line. So as h gets smaller and smaller and smaller, the rectangle on the right edge, the tall, skinny rectangle, is going to get thinner and thinner and thinner, but it's never going to get any shorter. The rectangle on top is going to get shorter and shorter and shorter without ever getting any narrower. The only thing that's going to get both shorter and narrower is the corner. So the corner is eventually going to turn into just a dot and disappear. But I'll have this line across the top. and I'll have this line across the side where change was made. And so I think of these two ideas as only changing these one at a time. So let's consider a mix and match idea. We started with these two functions and their derivatives were 3x squared and 2x respectively. I want to mix and match one regular function and one derivative. So we'll do these two. And we'll do these two. Multiply those. Derivative of f times g, derivative of g times f. What do you get? What's this product? Leo.
2x squared times x squared instead of being maybe 3x to the fourth.
Okay, and over here, I end up with 2x times x cubed.
2x to the fourth.
Hey, wait a second. Wait a second. Derivative I actually want to have come out, 5x to the fourth. The total change in my rectangle is the change across the top and the change across the side, and only one thing changes at a time. This idea can be generalized to any multiplication. So if I want the derivative of a product, the derivative of f of x times g of x, I do the derivative of the first one, leave the second one alone, then I do the derivative of the second one, leave the first alone. As a matter of fact, I don't like thinking of them as f and g. I like thinking of them as first and second, so f and s. And then I'll actually write, oh, it's the derivative of the first and then the derivative of the second. For the first, leave the second alone. For the second, leave the first alone. Ta-da! This is called the product rule. And this is a way that I don't have to multiply out the stuff that we did in problem 18. In problem 18, we had the cube root of x times 2 plus x. Rather than distribute, I can think of this as first and second and leave them like that. I think it's easier, though, to turn that cube root into a 1/3 power, so I remember how to do my derivative there with the power rule. Well, then, the derivative of this thing is the derivative of the first part. Leave the second part alone and add the derivative of the second part is just a 1. Leave the first part alone. With a little bit of algebraic simplification. Gathering your like terms after you multiply out the two pieces over there on the left, you'll see that this gives me the exact same answer you should have gotten on the homework for problem number 18. Is this easier or harder than multiplying it out in the first place? That's up to you. It sucks either way. I'll give you that. But what I will say is that the benefit to doing this with just the power rule is I only need one rule. Difficulty in doing it with the product rule is this doesn't look very nice. I understand that. Questions about the rule itself? You are not required to reproduce the where it comes from. You just have to remember the rule itself. I just didn't want you to think it fell from heaven, fully formed, sprung from the head of Zeus like Athena. Not a good idea. The reason this becomes important is this process of multiplying it out, like we did in number 18, doesn't always work. There is absolutely nothing I can do to algebraically make that function simpler. I'm stuck. It's not distributable. It's not combinable. It's exactly the way it's written is as algebraically simple as it can get. How do I take its derivative? Only accessible derivative option here is the product rule. I think if this is x squared as the first part and e to the x is the second part, and I just run with it like that. So, what is the derivative of x squared? And then I leave the e to the x alone. The next time through, I leave the x squared alone. What's the derivative of e to the x? Derivative of e to the x is e to the x. That's the sneaky one. It doesn't change. I'm done. This is not the answer they showed me in the back of the book, which pisses me off. Because what they did is they factored this. Took the e to the x out. And then they said, oh, look, I can also take an x out. Why would you do such a sick, twisted thing? There's a question on the homework that asked, where is my tangent line horizontal? How do you know when a line is horizontal? Heard it muttered. Set what equal to 0? The slope. The slope should be 0. Slope comes from the derivative. I set the derivative equal to 0. If you want to set that equal to 0, you're better off factoring it and setting this equal to 0. Because if the product of things is 0, one of the things has to be 0. So if I asked, where does this have horizontal tangent lines? The answer is wherever f prime is 0. And so I take this equation and I set it equal to 0. And I go to town. If this is 0, then either x is 0, or e to the x is 0, or 2 plus x is 0. Well, x equals 0 is already solved for x. If 2 plus x is 0, then x is equal to negative 2. What about this one? Say again? I got to take a logarithm to get rid of e. So grab your calculator. What's ln of 0? Several of you should be wearing very confused faces at this point.
If you get an error.
Error. Boom. It doesn't work. Why? Because the graph of e to the x never touches 0. It's got an asymptote there. So e to the x is never equal to 0. But the easiest way to do it is say, oh, I got to undo an e. I'm going to use an ln. I take ln of 0. My calculator goes, you can't do that. We should check and see if this is actually right. Grab your calculator and graph x squared e to the x. And we'll look for the tangent lines. Now, e to the x gets really big really quick when we go to the right and really small really quick when we go to the left. So if I look at this on the standard window, I'm not going to see very much, except some sort of a wiggly looking e to the x there. So I'm going to zoom in. Hit the zoom button. Option number 2 is zoom in. And if I hit enter right now, it will zoom in around 0, 0. I'm going to move up a little bit so that it lowers where it zooms, it recenters where it zooms in. I see a flat spot here. I see a flat spot here. 2 horizontal tangent lines. One of them over at x equals -2, one of them at x equals 0. Hot damn, it worked. Questions? Gesundheit. As I said with number 18, sometimes it's easier to multiply out, sometimes it isn't. So as the functions we are dealing with get more and more complicated, you have to make the decision algebraically. Would you rather multiply out? Will there be any benefit to multiplying out? I don't know in advance. Let's suppose I want the derivative of this thing. Should I multiply it out to try and avoid doing the product rule? Because right now that's first thing in parentheses, second thing in parentheses. My brain says, you should do the product rule here. But maybe if I multiply it out, I don't have to do the product rule. So I say to myself, well, let's multiply out. 2 times 1, 3 e to the x times 1, 2 times the square root of x, 3 e to the x times the square root of x. That term also needs a product rule, doesn't it? There's an e to the x times the power of x. And I can't combine those anymore. Phooey. There's no way to escape doing the product rule. So is this piece of algebra going to help me? No, don't do it. But did you know that in advance? Me neither. So you try. Did you do anything wrong? Nope. So you could do the derivative from here. And if I do the derivative from here, what's the derivative of 2? Because that's a constant. What's the derivative of e to the x?
Yes.
So I leave the 3, I do e to the x. Wait a minute, square roots. Square roots are x to the 1/2. So 2 square root x is 2 times, bring the 1/2 down, x to the -1/2. And here's where I need the product rule. 3 e to the x, the derivative is 3 e to the x, leave the square root alone. Then leave the 3 e to the x alone and do the derivative of the square root. As far as I am concerned, you stop right there. You've shown me you can do the derivative, and you've done it correctly. I'm good. Again, the textbook will simplify. And they'll say, hey, look, this 2 and the 1/2 are going to cancel. Negative power should go in the bottom. Here, the negative power should go in the bottom, but nothing cancels. So I still end up with 1, 2, 3, 4 terms. But I could do some simplifying. If I didn't multiply out, I do the derivative of the first part. Derivative of 2 is 0. The derivative of 3e to the x was 3e to the x. And I leave the second part alone. Add, leave the first part alone, and do the derivative of the second part. What's the derivative of 1? And the derivative of the square root of x, we've now seen that this will be the third time. Notice I still have 4 terms. 3e to the x times 1. 3e to the x times the square root of x. 2 times 1/2 x to the negative 1/2. And 3e to the x times 1/2 x to the negative 1/2. So I ended up with exactly the same thing. And it doesn't matter which one you do, because these are algebraically equivalent. A general statement. As long as your algebra is done correctly, which calculus rules you apply when are irrelevant. Both of those are perfectly acceptable answers. Questions? So something like x squared e to the x is kind of weird. But let me give you another one that I think is even more interesting. If I knew how to do this thing, I think this product would be very interesting. I don't know how to do this derivative yet, because I don't know how to take the derivative of the sine. Why is this an interesting function? Do me a favor and graph this one. You know what the graph of sine of x does, right? Sine of x goes back and forth and back and forth and back and forth. But e to the x does this. Since we're multiplying those together, what you get is something that's wiggling back and forth that's really small. And then all of a sudden it gets bigger and bigger and bigger and bigger and bigger and bigger. A vibration that grows out of control. If you go up Route 30 towards Pittsburgh, you'll get to the Westinghouse Bridge in North Versailles, just past the Goodwill and the bowling alley. And you'll be able to see the U.S. Steel plant off to your left. There's a sign on the Westinghouse Bridge. It says brake cadence. What the hell does that mean? What is cadence? Anybody been in the marching band? Anybody been in military, Civil Air Patrol, any of that? Cadence is your marching rhythm. You have to break rhythm when you go across the bridge. Why? I want you to imagine if we all started to stamp at exactly the same time in this room. I know, we'll all go sing We Will Rock You by Queen, right? What happens? The stands start to shake because everybody's bouncing at exactly the same time. If the rhythm you are bouncing with matches the frequency with which the bridge already waves, then those waves build each other up, and you get this. This has happened before in real life. The Tacoma, Washington, Tacoma Narrows Bridge is known as Galloping Gertie because when they finished building it, the breeze going down the river valley caused it to sway. The breeze got so strong, wasn't the right word, like so much reinforcement going on that the bridge shook itself apart. There's a video. They actually had cameras there, recorded the whole thing. Google Galloping Gertie. You'll find it. The video is amazing. I was most amused because Sony made a very cute commercial. There's a car on the bridge when it starts to shake. So they pictured the car shaking. They had this loud rock music playing. They showed somebody push the power button. They showed a picture of the bridge perfectly still. Sorry. This resonant behavior is what allows singers' voices to crack glass. They find the frequency with which that glass already vibrates, and then they sing at that exact note, and it builds up all the energy, and so once I figure out how this works, taking this derivative will allow me to look at the rate of change of that. And if I break the rhythm, if I break cadence, I don't keep putting more and more energy into the bridge. Useless, never going to see this anywhere. I have to drive across that bridge. Questions? We see functions that are products in all sorts of places. This particular e to the x sine x idea, this resonant behavior, shows up in chemistry, in amplification systems, in phase changes. It shows up in physics, in resonant frequencies. It shows up in molecular chemistry. Bond strength is based off of resonant frequency of the vibrating molecules in the electron orbitals. Ionic bond vibrations. I'll go with this. This is real life. And right now, engineering problems do a lot of this for tensile strength and torsion springs. In any case, you'll see this crap all over the place. Questions? What's the opposite of multiplying? So let's divide. Now it turns out, again, there was a problem on the homework. If I do f of x over g of x, that would be 1 plus x squared over x cubed. I know how to take the derivative of that if I simplify it. Because the bottom is a single thing, I can actually write this as 1 over x cubed and x squared over x cubed, which then I can simplify to x to the minus 3 and x to the minus 1, which means I know how to take the derivative. The derivative of x to the minus 3.
Negative 3x to the minus 4.
And in the same vein, I get negative 1, x to the minus 2, there. So if I can do the division and get something nice and easy to work with and just use the power rule, I'm going to do that. What if you do g over f? I can only split a fraction across the top, not across the bottom. I need a variation for the product rule. I need to somehow figure out how to turn dividing into multiplying and fix this. And there is a very nice way to do that. It requires me to do 4 more rules that I'm not going to get to today. But the end result is a formula that just comes out for division. So rather than go through all the convoluted derivation, let me give you the answer. I want to do this derivative. So let's think about this instead of g and f. Let's think about this as the top function and the bottom function. This is going to start very similar to the product rule. I'm going to do the derivative one at a time. Derivative of the top times the bottom, derivative of the bottom times the top. But the product rule was adding. Dividing is the opposite of multiplying, so we'll do the opposite. We'll subtract. But wait, there's more. If I start with dividing, I should somehow have dividing in the end. So I'm going to divide by the bottom thing squared. Notice that's not a derivative. I don't actually take the derivative on the bottom. I just leave it there squared. I promise in 3 more sections I'll be able to justify where the hell this comes from. But for the moment, let's see how it works. How do I do this derivative? The derivative of x cubed over 1 plus x squared. Take the derivative of the thing on top, and then I multiply by the thing on the bottom. I take the derivative of the thing on the bottom and multiply by the thing on top. And then I just leave the thing that's on the bottom again and square it. Whew. Now, the most common mistake made is to attempt to cancel. There's a 1 plus x squared here. I should be able to cancel it. Can't cancel it unless it's in both pieces on the top, and it's only in one of them. So if you want to simplify this, you actually need to multiply out all the stuff on top first. As you've seen, I've done so much algebraic simplification so far. I'm not going to ask you for it unless we need to do something with it, like where are the tangent lines horizontal? Maybe for some reason I don't want to know where they're horizontal. I want to know where they have a slope of 1. Maybe I want to know where they have a slope of 5. I can then go ahead and set this equal to 0 or 1 or 5 or whatever I need it to be. Wait a minute. I did that using the power rule. But that's still a quotient. I should be able to do that with this rule. And I should get the same thing. So let's check. Let's go back and do the derivative of 1 plus x squared over x cubed with this rule. What do you get when you do that? And is it the same as what we got before? What's the derivative of the top? And then we leave the bottom alone. Minus derivative of the bottom, leave the top alone, divide by the bottom squared. This is the same thing. Let's do some algebra. If I multiply this out on the top, I get 2x to the fourth minus 3x squared. Oh, and then minus another 3x squared. Wait, that squared is squared. That's x to the fourth. Cubed to the second. What's on the bottom?
X to the 6.
Notice I have two different things that are x to the fourths. So I'll do the subtraction. And now I'm going to split this up into two separate pieces. Minus 3x squared over x to the sixth, minus x to the fourth over x to the sixth. I'm dividing things that have the same base. What do I do with the powers? When I have the two of them, what do I do with the powers? I keep the same base. I subtract the powers. So x to the second over x to the sixth becomes x to the 2 minus 6. X to the fourth over x to the 6 becomes x to the 4 minus 6. Wait a second. Lo and behold, that's the same thing we got last time. Minus 3x to the minus 4 minus 1x to the minus 2. It did work and give me the exact same thing. Which is easier? I usually think that the power rule is a lot easier than the quotient rule, but as we saw, there are cases where I literally can't use the power rule and I have to use the quotient rule. So as we go along and develop more rules and new techniques, they get progressively uglier. I understand that. But what they also get is to give me more options on the way I do things. If I have more options, I can choose the most appropriate option for the problem. I would like you to find the equation for a line. What do you need to find the equation for a line?
First, we need to take the derivative of that equation.
Before I do any calculus, this is just an algebra question to start with, Leo. You're absolutely right. That's the first calculus step. But what are you getting when you do that?
Trying to get the slope.
Aha. Because to get the equation of a line, I need a slope and a point. I have a point. I need a slope. So to get that slope, what do?
I take the derivative of the equation and I plug the 1 in.
Aha. The slope of my tangent line is the derivative evaluated at 1, because the 1 is the x coordinate of the point in question. So I need that derivative. But here's the reason I need it, is so I can get the slope for my tangent line. So how do I get this slope? Oh, it's a quotient. Derivative of the top times the bottom minus derivative of the bottom times the top over the bottom squared. Now, normally, if I'm going to do something with this, my brain says I should do the algebra. But the thing I'm going to do is just plug in. So the hell with doing the algebra. Let's just plug in and see what we get. When we plug in 1, I get e to the 1 plus 1 squared, minus 2 times 1 e to the 1 over 1 plus 1 squared all squared. There, I've plugged in. Let's figure out what that number is. On top, I have e to the 1 times what? That's a 2. 1 plus 1 is 2. But then here I have 2 times 1, that's also 2, e to the 1. On the bottom, I have 1 plus 1, that's 2 squared, that's a 4. What's the top of this fraction?
0.
Because it's 2e minus 2e. That's a 0. And 0 over 4 is 0. So my slope is 0. What kind of a line do I have? A horizontal line. Yay! What is the equation for this line? That's what we were asked. I'll give you this part, but what number goes here? My slope goes there. Wait a minute, that means the whole right-hand side is 0, yes? The whole right-hand side is 0. That means the equation for this line is y equals a constant, which is matching what I think of when I think of a horizontal line. Y is a number everywhere. That just happens to be this sucky-looking number, e over 2. The fact that this sort of a problem used the quotient rule doesn't mean I can't also do this same problem with just the power rule or the product rule or any of the other rules I'll eventually get. Finding the equation of a tangent line is a useful thing to be able to do regardless of what rule I need to use to do it. However, I really do need some more rules. I still have all the trig functions to deal with. I still have other types of functions I don't know what to do with. But I'm not going to do that Monday, because Monday's the exam. On Monday, everybody gets their own separate table. You need to sit with at least one chair's room between you and the next person, and then we will take the exam, and then you will go about the rest of your week and not panic. I believe there is a review session over the weekend. There might actually be more than one. So go to it, do what you can, see everybody. I will post all of the keys right now, and I will see you all on Monday. Have a wonderful weekend.